Here we have a square disc with corners labeled 4, 1, 2, 3. We're going to consider the starting position of the disc to be just this, where we have the 4, 1, 2, 3. Now on the flip side of the disc, where we've got 1 here, if I flip it around there, we've got 1 prime. Now I'll keep my fingers in the same corner and turn this so you can read that. But that's 1 prime. On the other side of 3 prime, what do we have? We have 3. So that on the other side of each of these numbers is the corresponding number, but with a prime, that is an apostrophe, which we read as prime. Now if we go back to the starting position, we're going to look at rotations of this disc. M is the rotation that goes 90 degrees clockwise from the starting position. So if we go 90 degrees clockwise, we end up with 1 and 2 on the bottom, 3 and 4 on the top as we move around clockwise. So M, if we start at the starting position, the rotation M will be represented by putting 1, 2, 3, and 4 around the square, same order that we have them. Now from the starting position, 180 degree rotation, there's 90, and there's 90 more, that's 180. Now of course the numbers come out upside down, but we're not going to worry about that. We're just going to write the numbers where they are. We have 1, 4, 3, 2 as we go around counterclockwise, starting at the bottom corner, and there's N. P is going to be a 270 degree rotation. So if we do the P rotation, we do 1, 2, 3 90 degree rotations, leaving us 1 and 2 across the top, 3 and 4 across the bottom, as you see. So we can write down what that one looks like. And the Q rotation will be through 360 degrees. Well, that's another 90 to what we just did. And of course that brings us back to our starting position. Now we have other possible symmetries of this square. We have the R rotation. Now what R does is it flips the disc about a horizontal axis. So we imagine an axis passing through the disc in the horizontal direction. If we grab the disc at the ends of that axis, or where the axis touches the edges, and flip it, we see that we get over onto the other side with 1 prime, 4 prime, 3 prime, and 2 prime. S is the rotation that we get, or the result that we get, if we rotate about a vertical axis. So from the starting position, we grasp the cube here and rotate it this way, and we end up with, as you see, 1 prime, 4 prime, 2 prime, 3 prime. Now I haven't really left myself enough space here. I wasn't thinking ahead that well, but I think I can put T in here. And we'll designate, or we'll describe T by going from the lower right to the upper left. If we do that rotation, we rotate about the axis from lower right to upper left, and we get this. And you can see where those numbers are. We have 1 prime, I'll have to label it outside here, 2 prime, 3 prime is here, and 4 prime, which I can't really label very well. This is going to be hard enough for you to read, but 4 prime will be right here. And then we have the final rotation, the V rotation. A rotation about the upper right to lower left axis. And if we do that rotation, we see that we end up with 2' and 1' and 4' and 3'. Now hopefully those are going to be visible enough. We can make a table, and I'm not going to make the complete table because obviously that's going to take a fairly long time. But if we start here, an M and an M rotation, well, the M rotation is a 90 degree, the N rotation is another 90 degree rotation, and that's just going to be the same as a 180 degree rotation. So that an M and an N is going to give us an M and an M, a 90 and a 90 will give us a 180. So that's fairly straightforward. If we did an M and an N, well, that would be a 90 and a 180, which would give us a 270, which is the P rotation. And M 90 degrees, P 180 degrees would give us a Q, which is 270. And there's something really wrong with this table. I'm sorry. A 90 and P's a 270 would give us a 360. And then an M with a Q, which is a 90 with a 360, would just give us the same thing, a 360. That is, a 360 is equivalent to 0. 360, we just go around and come back to wherever we started, so that we're going to get this result. Then if we go on and make the columns of the table, it's fairly simple. We're just adding 90s and 180s and 270s and 360s to get 90s and 180s and 270s and 360s. So this table ends up looking a whole lot like a table for addition mod 4. Now there are similarities and differences. The identities over here on the 4 element, the 360 degree rotation, which is equivalent to 0 degree rotation. But you see that if we just look at this part of the table, we do have an identity. Q is the identity. The 360 degree rotation, wherever the thing is going to leave us in the same place. If we start here and go 1, 2, 3, 4, we're back where we started from. We can combine, of course, the rotations with the flips. So for example, if we wanted to do P and then T, let's see what P and T would give us, and that's going to give us something that we would put in the P row in the T column. So let's see, a P rotation is 270 degrees. So we go 1, 2, 3, that gives us 270. And then a T is a flip about this axis. Okay, right there's our picture of the T rotation. So if we flip like so, where do we end up? We end up with the 1', the 4' on the top, the 2' and the 3' on the bottom, which is the S rotation, isn't it? So that P and T gives us S. It would be interesting also to see what maybe would happen if we reversed these. Instead of doing P then T, let's do T then P. Now the T is a rotation about this diagonal. Here's our starting position. If we then do the T rotation, we end up here, or the T flip. And then the P rotation is a 270, so we go 90, 180, 270, and where do we end up? Well, we end up with the 1' and the 4' on the bottom, the 2' and the 3' on top. Which one is that? Well, it looks like that is the R rotation, isn't it? The 1' and the 4' here, the 2' and the 3' here. So if we do T, then P, we get R. Now this tells us something about whether the operation is commutative. We reversed the order in which we did the flip and the rotation, and it gave us a different result. Now you could make your own. You can take a floppy disk if you have one and label it, but you can make your own square and check out these rotations. But this is how the table is arrived at. And again, we notice that Q, the 360-degree rotation, which I think your text calls a 0-degree rotation, which is just fine, is the identity because it's not going to change anything. Wherever you end up, if you then do Q, you're not going to change your position. You're just going to go around the circle one time. So that Q is the identity here and here. We can ask if every rotation has an inverse. We could check for commutativity. We already did and showed that it's not commutative once you get down here, although it is commutative in this part of the table. And we could check for inverses, associativity, and so forth. So it's a very interesting set of symmetries. These are actually called symmetries of a square. Okay, we can do rotations through 90 degrees. We can do flips about any of 4 axes and get some very interesting results.